Okay, thank you. I'm Dave Carrott. I'm a security consultant, pen tester from Wellington in New Zealand. For those who don't know where Wellington is, we're up the top of the map there. I enjoy sort of the radio hacking and also the physical stuff for Flock Sport and stuff like that. So today we're going to be looking at GPS, GPS spoofing, sort of how we can change time and what we can do with that, attacking some NTP servers, and whether we can actually detect some of the spoofing. So just going back to the start, GPS, it can tell us where the time is, tells us where we are, and it uses the time to actually do the calculations to figure out where you are, and it's a constellation of satellites orbiting at about 20,000 kilometres above us. So we have to trust GPS, right? So does anyone currently not trust GPS locations? Anyone not trust GPS time currently? Does anyone feel they may change their opinion by the end of this talk? Sort of we have to trust GPS, right? It's too important to life. It's got to be robust. The military uses it. Important services like Uber and Tinder and stuff require it. And also some other less important things like NTP time, planes and ships navigating, keeping an eye on armoured vans, and the taxi. We've just changed our taxi law in New Zealand, and they've removed the knowledge requirement for the drivers because the Minister of Transport came out and basically said, what was the last time you ever saw a taxi driver without a GPS in their car? And from my experience, actually, since taxi drivers have got GPS, they've actually become worse at actually getting to where you need to go. So moving forward, look at some of the attacks. There's sort of been GPS jamming for a while now. In this particular instance, a truck driver, their manager had put GPS trackers on all their trucks, so he didn't like being tracked. He also liked having an afternoon nap. Happened is his particular nap spot was next to Newark Airport, and when you mess with planes, people do sort of notice and they'll come out and actually track you down. And also on the GPS jamming front, apparently some of the black cabs in London, they don't like Uber and Lyft, so they're running GPS jammers to mess with Uber and Lyft, so people will use the black cabs rather than actually Uber and Lyft. But jammers are rather boring. You can just buy them off your favourite Chinese online store. They're not particularly graceful. They just sort of jam GPS. You realise that, hey, I don't have a GPS location, something's amiss. Moving forward to sort of 2011, supposedly the Iranians crashed the US drone by doing some GPS spoofing to try and get it to land or crash land in Iran, though this was nation-state level of cash and research. Moving forward to 2013, a professor with some students and $2,000 worth of sort of equipment managed to steer a ship off course. This wasn't GPS spoofing per se, it was the fact that they delayed the GPS time signals ever so slightly that the boat thought it was somewhere where it wasn't, so it altered course trying to correct itself. In May last year, Unicorn team talked about using wireless time signals to and attacking NTP with this. They looked at GPS, they also looked at some of the other terrestrial time sources that are sent out over radio, though from what I could see, and they didn't actually release any code. Then I found this on GitHub. Someone had written a software-defined GPS signal simulator. So I took that, added in in addition to that, you need a computer to run it on, you need a software-defined radio with transmit. I personally used the Blade RF because that's what we had sitting around the office at the time. Also the Hack RF or the USRP will also work. So for less than $500 in hardware, you can start your GPS spoofing. And as far as software-defined radio things go, this code, you just downloaded it, you ran it, and it just worked fine straight out of the box. Sort of one of the best experiences I've had with software-defined radio code, which is really nice. Yeah. I also had it running off a Raspberry Pi 3. In that case, with a battery, actually the Blade RF was about the biggest thing involved in the setup. The regulators generally don't like you trying to broadcast GPS signals, so best to wrap it up in a Faraday cage with some aluminium foil. Not a lawyer. It's not open spectrum. You've got to keep your GPS goodness to yourself, unfortunately. And when you are doing this, your software-defined radio transmitter is going to be a lot closer than the satellites. Satellites are about 20,000 kilometres away. You're going to be a lot less than that. Though, from what I've seen of other people using this tool, the range is still only hallway length. It doesn't go particularly well through walls. And GPS signals on the whole are actually quite weak. So on the left there, we've got a normal radio signal. We have, in the red there, we've got the noise floor, so that's just the background static. And then in the green, we've got the signal. So grossly simplifying radio stuff, in this case, we can basically figure out what the noise floor is, delete it, and you're left with just signal. But on the right-hand side there, we've got the GPS, and it's the other way around. In red, we've got the noise floor, and below the noise floor, we've actually got the GPS signal. So that's why GPS processing uses so much battery power, because it's actually having to process all the noise, hoping to actually find a GPS signal. That's basically got a mask, and it goes, is that a GPS signal, or is that a GPS signal? And when it does detect one, it goes, oh, yep, I do have it, and it can start actually processing it. So we've got the simulator software. I've got a Blade RF. What could we do? First simple thing, we can just change our location. My phone was under my desk in the office in Wellington. Here I've got my phone, think it's actually in Bletchley Park. So how does the tool work? It had two methods of working. The first one was a two-step process where it would generate the data and then it would broadcast it. It works out about 1 gigabyte of data a minute. And it can be a standard location or it can be a path, so you can actually have the GPS location moving around. It also takes in the almanac of where all the satellites are going to be at a given time, so it's not generating just one GPS satellite, it's not generating the entire constellation. It will go, at this place on Earth, it should be seeing this set of satellites at this particular time. And the other method, it does both the generate and the broadcast in one step in real time. Though this does have the downside, it needs much more CPU to actually do this. So little limitations of the tool. By default, it will only generate 5 minutes of data at a time. With that, you can just go into the C header file, change it, and you can do longer. I suspect the reason for this was didn't want bug requests and complaints saying this thing filled up my disk when I was trying to generate 2 days worth of data. It means that hopefully the person who knows how to change a C file also realises about file sizes and stuff. The Raspberry Pi 3 can't do the generation in real time. It takes, if I was trying to generate 5 minutes of data on a Raspberry Pi 3, it would take about 15 minutes of actual CPU time to generate that 5 minutes of data. And also generating a path is quite simple. You add sort of 0.1 second intervals, you give it a set of locations. Unfortunately, you can't just use latitude, longitude and altitude. You have to use Earth-centered, Earth-fix or NEMA data rows at this, but there are tools to do the conversion online for you. So it becomes quite simple and you can start drawing little paths in the middle of Wellington Harbour using the tool. So what can we do with the location spoofing? Armoured van, you want to take it back to your underground lair, broadcast the path that it should be travelling around all the banks, but you're actually driving it off to your underground lair. Uber has a time and a distance component. If you never left your actual destination, it's only ever going to have a time component. And given experience with Uber drivers and stuff, they're never going to. They always blame me and saying, "Oh, the map's really bad," or "It's giving me bad routes today." They're just going to assume the app's having a bad day, they're never going to sort of assume someone's actually attacking them to scam money out of them. Planes can also use GPS for landing, particularly when it's not a straight landing and you can't use the normal terrestrial-based radio stuff. This is Queenstown Airport in New Zealand. It's got a nice hairpin, a little chicane onto landing through some tight valleys and stuff, so you want the planes navigating fairly accurately through that, or they'll make a big mess on the side of a hill. Also, we can change time. Seeing one of the core things that GPS is actually spitting out to do all the calculations for locations is its time. So we have NTPD, which is the common NTP daemon on Linux and Unix servers. If you have the GPS receiver, it's just putting serial into the computer, NTPD knows how to do the rest and actually uses a time source with no really additional config required other than adding a new server in the config file. Also looking at some of the commercial NTP servers available on the market that do have GPS in, they will appear to run NTPD under the hood, and because NTPD has its own custom license, so they have, and then if you're in the documentation, they mention they've got stuff licensed under the NTPD license, vis-a-vis they have NTPDs running under the hood. So a little bit of tacking NTP. If you try and move time in big amounts, particularly over 5 minutes, NTPD will shut down. Though there's actually no log messages saying why it shut down. And when you restart NTPD, it just says the time has been changed, which is really common because the local motherboard clock and NTP very rarely actually correspond with each other because motherboard clocks are notoriously inaccurate. And always trust the GPS time or the NTP network time over the motherboard clock. If you do turn the NTPD logging up to sort of debug level, but no one actually runs this in production like this, there is some logging which I could kind of interpret what was going on because I was actually attacking it at the time and knew what I was doing, but if someone saw this and actually in real life they wouldn't think much of it. And if NTPD crashes and it restarts through a watchdog, or the sysadmin has to get up at 2 a.m. in the morning, and it just restarts normally, and it continues on, they're not actually going to look any deeper or actually check the time is correct a lot of the time. I just want to go back to sleep. But we want to somehow move this time without actually crashing NTPD, because if we are actually attacking it. And so we have to, instead of doing the big steps, we have to do lots of little steps back in time to sort of wind the clock back. So I wrote a tool called Targips. It's a Python script, wraps around that sort of method 2 of the GPS signal simulator. The code's up on GitHub currently, and this is sort of designed mostly for air-gap networks. So a network where you've got the NTP time servers, it's getting the time from GPS, and there's no other network connection out to the rest of the world to get a time source from anywhere else, or people who have sort of configured it badly with maybe only GPS and one other server, and then in that case it will most probably trust the GPS time more than the other one because it will have a lower stratum coming from the GPS satellite. So sort of my little test setup I had was a little hacker on his laptop broadcasting out the GPS signal, and then down the bottom there I've got an NTP server receiving the GPS signal. So I've got a little sort of video of this. So the local machine up on the top left, that's the attacker. The target machine, that was the NTP server on the top right, and in the bottom there we're actually going to have the script running. So the script's running away. So it takes a little while, and as the script's running it will sort of move time backwards, let it sort of give it time for the GPS receiver to sync back up, let it run forward a little bit, and then it will move the time back again, wait for GPS receiver to sync up again, and then play for a little bit, then move the time backwards again. So it stayed rather stable. You could move the time back a lot through this method, and it's just running like this. So moving on. So what can we sort of do with these sort of, if we could change time, what sort of attacks can we do? Most of you have most likely come across time-based one-time passwords, like you'll see in Google Auth. Every 30 seconds you get a new token to use with your login. So in this case, if we can move time backwards, what can happen here? So I've got a little video here. Is it playing? Yep. So just getting the current date there. SSHing in, and here I've set up SSH to require the verification code in addition to the password. So there we've logged in. So now sort of going to fast forward, just copying the time just so we can reference back to it later. And now the video is going to fast forward a little bit. So we've got the times moved forward a little bit. So we'll just wait for that to happen. Going forward. Yeah, so I'm checking the date again now, and we've seen that the time's moved forward. So we will log in again, and the first time I log in, I'm going to use the code we used before, and we'll see that we get prompted again for the password because it's the incorrect one-time password for this particular time. Yeah, so it's prompted for the password again, but if I type in the password and then use the current verification code, I can log in. So I'll log out again, and I'll fast forward it again, but this time while it's fast forwarding, I'm actually going to be moving time backwards again. So the video's fast forwarding, time's going to start winding itself backwards after a little bit. So yeah, so we see time's moved back a little bit, and just waiting for it to now tick forward to where we logged in last time, or the very first time, sorry. Yep, so the time's in sync, so we can SSH in again. Type in the username and password, and use the same code as before. And we've logged in. So this is the default libpam Google Auth sort of time-based one-time password library. Thing was when you're setting it up, it didn't have a default for reuse. So this is the question it had for reuse. If you just hit enter, it would just prompt you again with yes or no. It doesn't actually say, yes, you do want reuse protection on, because it stops. You know, they may be assuming that time only ever moves forward. You won't be able to reuse it if time moves backwards. So that was the case. I've also looked at some other implementations. I've got some add-ons to websites and things, and then some of them do have it by default, some have no default, and then on the right I've got some common libraries available, and in this case only one of them actually had the reuse verification in it. The others didn't even have that function available. They just obviously assumed time moved forward. Yeah. So when you are looking at implementing time-based one-time passwords, make sure there is a setting for disabling reuse, and make sure it's set not to allow reuse. Or you can look at other two-factor auth alternatives. There's HOTP, which takes a counter plus the seed to give you the number. There's U2F, which is currently what I prefer if it's available. And also friends, don't let friends use SMS for 2FA. So I was also looking at what some of the other things in Linux that uses time. So something called sudo, which allows you to escalate and run something as root, and that will prompt you for a password, and then if you try it again in the next 5 or 15 minutes, it won't prompt you again for the password. So I thought, hey, can I sudo, let time run forward, roll time backwards, and then can I still log in? In this case, sudo didn't realise what had happened and stopped it. And this is because instead of using the wall clock time like libpam was using, sudo's looking at the number of OS ticks coming from the CPU. So it's actually known so many ticks have passed, therefore I need to re-authenticate the user. Uptime works in a similar way, so I can sort of use uptime as an example here. So we've got a date initially on the 7th of November, the server's been up for about 4 minutes, I roll the server forward in time a week and it realises, hey, it's only now still been up for 7 minutes, only 3 minutes have passed between me doing those 2 snippets. Forensics could get rather interesting. If you had a log consolidator that allowed you to sort all your logs by time, the logs might have the earliest log entry saying the hacker logging out, then the hacker doing the elite hack, and the most recent entry is the hacker logging in. An IR person may initially start from when they logged in and started looking forward to see what happened. They mightn't necessarily actually look backwards to see what happened in the past before their initial login. Also, if there's not centralized logging, you could just, with a cron job, move the date backwards and forwards at random, and this may actually cause the log rolling and log purging to happen on the server that, oh, a week's passed, I better go and purge and delete all the logs. And a couple of weekends ago, someone saw on Twitter, someone had mentioned that they'd seen in a Stingray release, one of the Stingray device release notes, that that sometimes when an external GPS device gives erroneous GPS ticks, the license for the Stingray may fail. So there's, you know, maybe if you're in a jurisdiction that allows GPS broadcast and you want to disable a Stingray device, maybe that's a method to try. So what's sort of the NDP servers and actually how do they work? On Data Center roofs you may often see a GPS aerial that often looks like that. And sort of these work in 2 ways. At the top, you either have the GPS antenna and it's radio down the cable down to your data rack and into the computer. And then actually inside the server, you've got the GPS receiver, and that's directly soldered onto the motherboard. And the other option is you have the GPS antenna, and that's also got the GPS receiver up on the roof, and then it will send serial down through the building, down to the rack, and into the GPS server. And to use that, you just tell NTPD that you've got a new server, 127.0.20.0, and then that NTPD knows, oh, that's a GPS source, I'll look at dev GPSO and dev PPS0 and start doing the import for time. So the serial data is the NEMA data rows. The GPS ones start with $GP. Those are the 2 sort of most common ones used sort of by NTPD for time, and you'll see they've got a time component, and one of them also has a date component in it. And the other, there's an additional wire quite often involved, and that's a pulse per second signal. And what that means for the 0.1 of a second, at the start of a second, it'll go high for 0.1 of a second, there'll be low for 0.9 of a second. And a pulse per second doesn't contain a time value, it only gives a very accurate indicator where the second starts. And the way the GPS receivers are built and designed, the pulse per second takes a much shorter path through the processing and has less processing on it, so it's a much more accurate time sort of indicator and gives you sort of micro or nanosecond accuracy opposed to the NEMA data sentences, which are maybe only millisecond accuracy. So in the setup I initially just had NTPD running on Raspberry Pi. I had the GPS receiver coming in through serial onto the GPIO pins along with the pulse per second. So initially I started looking at can I just spoof the pulse per second? It's nice and simple. It's just highs and lows. Don't have to think too much. So I connected the pulse per second wire to another GPIO pin on the Raspberry Pi, and I just had a little script that set the pin high and low as applicable. What I found out was happening was if you run the pulse per second sort of faster or slower than the NEMA data, it would sort of keep correcting itself as it would get the actual second number from the NEMA data rows, but just the start of that second might be a little bit messed up. So never deviated more than a second. If you're in finance or telecoms or energy where fractions of the seconds count, it would be an important thing. In other industries where seconds aren't, the actual fractions of a second aren't so important, it's most probably less of an issue. So I thought, can I just remove the serial data and will it just rely solely on pulse per second? Pulling the wire, it didn't, it just stopped, and it even started disregarding the pulse per second in that case. So I did have to actually start working on getting a full solution that did the NEMA data and the pulse per second. So I've got another Python script that will do that. Just like TarGIPS, it will move time back slowly and in steps, so you can adjust the time. I found this simpler to use than TarGIPS because I wasn't having to deal with the GPS signals. I was only worrying about serial data, and it's a lot simpler to write serial than it is to try and integrate with other tools and involve radio and the timing involved in that. So the script basically worked by writing some NEMA serial to standard out, have a pulse per second pin going high or low, loop through that at whatever rate you wanted a second to be, use SOCAT to move the standard out to the relevant virtual console, then symlink the virtual console to dev GPS 0, and NTBD top the time from there. So behaved just like TarGIPS, simpler because it didn't have to involve the radio, though does require physical access to the data center's roof to actually splice into the wires rather than attacking it remotely. So I went and got an NTP server. This is a cheap one that the boss paid for. On the website it says that this company delivers NTP solutions for things like airports and nuclear power plants, and so this should be good, right? Nuclear power plants, got to keep those safe. So with TarGIPS and NEMA desync, if I move time forward in just one big jump, it just continued on merrily. If I moved time backwards in a big jump, it crashed like we saw in NTBD before, but TarGIPS and NEMA desynced worked fine and it could move time backwards on it. So I had no protections in that regard. And then I also had a look at the web UI, found some bugs. They're so simple and dumb, I'm almost afraid to actually mention them here. But basically found that, hey, it's using get for everything, so even when you log in with a password, it then just puts the password up in the URL bar. And basically because it's not using cookies at all. So I could just later just navigate directly to the relevant pages. And you notice when you want to change the first one was changing the network settings. When you go to change the password, you're actually in a different password form. This case, password form. And when you reset the password, again, the new password's just in the get. I didn't find any posts in it. Having this URL is really handy when you do change the password, then come back to the thing a month or two later and forgot what you set the password to. You just pull out the URL and reset the password without needing to actually know the current password. So, auth bypass by not having any auth, I suppose. So sort of we've been looking at some attacking. How about we can look at maybe some detecting of the GPS spoofing? Have a little tool called GPS Snitch, and how that works is it looks at the time offsets from, in this case, if you do have external time source other than just GPS, you could look at whether the time you're getting from GPS differs from the time you're getting from the NTP network. You can also look at, say, the signal strengths, because when a satellite's directly overhead, it's going to be stronger than when it's down at the horizon because the distance is greater, and also the range of the signal strengths, because different strengths of the satellites, you should see a different range and the signal strengths. And also, if it's an NTP server, the location should be stationary. Most people don't have data centers that move much. And also, one that I haven't actually looked at is maybe looking at actually the direction of the signal, because if you're doing GPS spoofing, chances are the signal's all going to be one direction. When you are using GPS in the real world, the satellites are all around you. So I got a little video of the tool running. So what you see, it's ticking through, and initially it's only going to do warnings. This is because we want to remove any false positives, because sometimes if a cloud goes past or other little things like that, the GPS signal will change suddenly, and we don't want to alert every time a cloud goes past. So we'll wait for a particular number of failures, and also more than just one type of failure. So by the end of it, it's actually saying there we go, it's saying actually critical, and it's detecting the error now, the spoofing now. So that's particularly helpful maybe if you're running a GPS server. If you just stop looking at the GPS location bit, you could also use it in a GPS receiver. So how can we detect the NEMA serial spoofing? So this is a new tool I wrote just for DEF CON. Hopefully it's on GitHub. If my colleagues have woken up at 9 AM on a Saturday morning, they should have made this repository public. So if not, it should be public soon, but it is there waiting to go. What this tool does, it records as all the NEMA sentences coming in, it looks at the time and it timestamps them all, and it looks at the ratios between the different NEMA sentence types, and also how many sentences per second it gets. So just a little table there. Most of the sentences are coming in once per second. There's one there that sort of only comes in every 0.6 of a second. So if you start to see this the sentence rate deviating from 1 and sort of the ratio changing, you know that something's amiss in this case. And yeah, when it sees those differing, it will alert for you. So we've got those tools to detect and maybe stop the GPS spoofing. Some other methods is making sure you have more than 3 upstream NTP servers. The number of servers I've reviewed in my day job that only have 1 NTP server, even better when they have 1 NTP server configured and that server is no longer actually working. Yeah, if you've got 3, you can detect the bad ticker and you know which one's actually ticking bad because you still have 2 corresponding. And also make sure you've got multiple types of upstream. Don't rely just on GPS. There's also atomic clocks, the NTP pool. And also don't pick one upstream provider for your time outside of your network, because you might have the rogue admin problem at the upstream, who they could change all the times on their internet facing NTP servers, and then all your time goes awry. Yeah, that's a particularly common case if you're using if you're a customer of a managed service provider and they just provide their own time servers into your own network. You maybe like to say, hey, can we also get some time from outside so we're not reliant solely on you for time. If you're on an air-gapped network, and you're still relying on GPS, well, you're still receiving some signals over the air, so are you still really an air-gapped network? Maybe in that case, splash out, get some atomic clocks or some cesium or iridium, and yeah, do it like the national labs that run some of the central time servers around. if you're actually deving some NTPD or something, maybe look at implementing something like GPS snitch and NEMA desync. Make the logging a little bit more explicit when it is shutting down because the time's so different. And yeah, so that's my talk. Thank you very much. Thank you for coming.